Now let's look at some prototypical phase diagrams. The two that people always use are carbon dioxide and water. So let's look at water first. This is from a Wikipedia article. The blue phases here, or the blue area, is where the water is a solid. The sort of orangish yellow is where the water is a vapor. And the green is where the water is a liquid. Here's the critical point of water where all three phases coexist, the solid, the liquid, and the gas. That's at 0 Kelvin and 611, so a little lower pressure than 1 atmosphere. 1 atmosphere in SI units is 100 kilopascal, about. See, 101.625. Okay, so that's the atmospheric pressure. So the triple point of water is 0 Celsius, but lower temperature than atmospheric pressure. So you want all three phases of water to coexist. At 1 atmosphere pressure, that's that line here, this is the melting point of water at 0 Celsius, right there. And keeping it at 1 atmosphere at 100 degrees Celsius, we have now the boiling point. So this is called a normal boiling point. It's the point at which, at 1 atmosphere, there's a phase change from liquid to gas or gas to liquid. And this would be the normal freezing point at 1 atmosphere, the temperature at which you have the solid-liquid phase equilibrium. The critical point of water is way up here. Note that this is a logarithmic scale. So it's about 1,000 times, let's see, 10 to 1,000 times higher pressure than atmospheric pressure, the critical point of water, way over here, and it's 350 C. So above this temperature, you do not have that phase transition. And finally, you might notice that there are other phases of solid. So solid just doesn't have a single, of water, doesn't just have a single solid phase. There's other phases. This phase is called IH. That's the normal thing when you think about ice, when you put ice in drinks and so on. But there's an IC phase. There's a phase called 11, and so on. So you can have phase transitions, solid-solid phase transitions here. For those of you who are interested in Kurt Vonnegut's stories, this is one of his stories of Cat's Cradle. And this is ice 9. So he postulated in Cat's Cradle, or actually said that there was a form of ice 9, that was thermodynamically more stable than liquid water. So if a little bit of this got out and got into, say, the world, the whole world at room temperature would, the water in the world would change to ice. Ice 9 does exist, but it does not have the properties that were described by Vonnegut in his novel Cat's Cradle. Another interesting point, maybe you can't really see this, but if you would blow this up, this has a negative slope. So the phase transition line between solid and liquid has a negative slope for water. What does that mean? Well, normally you think of a liquid, and if you increase the pressure on a liquid at constant temperature, you would think, well, I'm forcing those things together, and then the liquid would change into a solid. But water is different. If you put additional pressure on a solid, you would think it would remain a solid, but no, it becomes a liquid. So that solid compressed in this region here becomes a liquid. That's interesting. And I guess that's it for the phase diagram of water. Let's look at the second one, the phase diagram of carbon dioxide. So this is CO2. All right, just take a look here. We have the liquid, the gas, and the solid. Probably some other forms of solid, but we just lump them all together here. There's the triple point of carbon dioxide. This is the point at which solid, liquid, and gas completely coexist. It has a degrees of freedom of 0. Here's a solid liquid line, and here's a liquid vapor line, and right there is a critical point of carbon dioxide. What's interesting about the critical point of carbon dioxide is that it's around 300 as opposed to, 300 Kelvin. This now the temperature scale is in Kelvin. So this is around room temperature. Oh, that's kind of cool. And the pressure here is, well, not too bad. This is 1 bar here. So you have to go about 100 times 1 bar there. So that's around one atmosphere. You go to about 100 times atmospheric pressure, you get the critical point. So if you raise, here we are at, say, 300 K, If you go a little bit above 300 K, you go here, you go into the regime as you start compressing gaseous carbon dioxide, you go in the regime of what's called a supercritical fluid. And you get supercritical carbon dioxide because you're above the critical pressure. Supercritical carbon dioxide is a good cleaning fluid. In fact, as some people propose, instead of using toxic chemicals to do dry cleaning, why not use supercritical carbon dioxide? And also, if you're into decaf coffee, supercritical carbon dioxide is a good way to remove caffeine from coffee beans. And so when you look at, various ways of taking out caffeine from coffee, one of them is called, using the natural effervescence of something or other. What they're using is supercritical carbon dioxide to remove caffeine. That's it for carbon dioxide. And I guess that's it for this particular part of Lecture 10. The next lecture we'll talk about phase thermodynamics.